Hi, welcome to today's little sojourn or little wander through general solutions of trigonometric equations. Okay, and that's very much what it is. It's general solutions of trig equations. Now, we've obviously been looking at a range of problems which involve sine, cosine, and tangent functions, and maybe not so much the tangent functions. Yeah, we've sort of looked at tan, but primarily sine and cosine. As it says here, we've looked at sketching graphs, changing periods, changing amplitudes, finding equations of trig functions given graphs, and solving trig equations. Now, generally speaking, when we've solved those trig equations, for example, cos theta is equal to half, we've always then been given a domain. So we've been told to, for example, solve it between 0 and 2 pi. Now, when we have that situation, we know that generally speaking, the cosine curve always has two solutions between 0 and 2 pi because the period of cosine. We're looking, therefore, for two solutions. What if we wanted 22 solutions? What if we wanted 102 solutions? What if we wanted every single solution under the planet? Highly unlikely in a VCAR exam they're going to ask you to find every solution under the planet. Ha ha, he says! Well, not the specific solutions, but what if we could come up with a way of working them out? What if we could come up with a way of general solutions, for example? I mean, we have the general equation of a quadratic formula, x equals minus b plus or minus the square root of b squared minus 4ac over 2a. So, actually, that's what this lesson is going to be dealing with. We're going to be looking at finding the general solutions for sine, cosine, and tangent functions. And obviously, let's start with a standard cosine curve over two periods. Now, what we notice is, if I was trying to find, and using that example earlier, as cosine theta is equal to a half, what you've got to realize is that we always have cosine equals y. We always have equations as y equals. Although we swap which side the cosine is on, and yes, more traditionally, we would have y equals the cosine of theta. When we have cos theta equals a half, what we're actually saying is, draw a line along the graph when y equals a half, and this just so happens on my graph to be y is equal to a half, and find all the points where it crosses. So, looking at my graph here, what do we find? Well, our calculator normally gives us that first value. So if I was to put inverse cosine of a half onto my calculator, the cosine minus 1 of a half onto my calculator, out would pop pi on 3. If we weren't using our calculator, I could use my two triangles. We would then be going, oh, okay, so I've now got to use all stations to Canberra. So here is my all stations to Canberra. All stations to Canberra. I know that cos is positive, so it's got to be in this quadrant here and this quadrant here. I know my reference angle is 1/3, pi on 3, so that has to be pi on 3. Not quite at 2 pi, so if I do 2 pi minus pi on 3 gives me, oh, that's going to be 6 pi, so that's 5 pi on 3. So there's my second solution. Yay, there's my second solution. And we would know to then find all other solutions, I would add on 2 pi. So if I keep adding on 2 pi to each of those two successive solutions, I will end up with, the next two solutions. So 4 solutions for 2 periods. And if I kept adding on and adding on and on, I'd get more and more and more. And generally speaking, this is the basis for finding the general equations of these trig functions. So we knew that the first solution was pi on 3. So we knew that first solution was pi on 3. There's also another solution at minus pi on 3. Why? Well, the symmetry of a cosine curve would suggest that if this is coming down here like this, that point there would be minus pi on 3. So I'm going to group those two together. The next one would actually be 2 pi plus pi on 3. And I suppose if we were to take this equation here and add 2 pi onto it, it would be 2 pi minus pi on 3. Next two solutions, well, I would have taken this value here and added on another 2 pi, which would have given me 4 pi plus pi on 3 and 4 pi minus pi on 3. So all I'm actually doing to get from each of these successive pairs to the next pair is add on 2 pi. I'm writing it out longhand because hopefully you can start to see that there's a bit of pattern. So if I actually call these my 0th solution. Now you're going to turn around and say, what do you mean by 0th solution? In maths, generally speaking, we like to use integers. And why do we like to use integers? Because they are the numbers 0, 1, 2, 3, and minus 1, minus 2, minus 3. Now, the reason we like 0 so much is because it actually gets rid of a load of stuff. You multiply by 0, what happens to it? Well, it disappears. So this one here we'll call my first. This one here will be my second set of solutions. So they're my 0th solutions, my first solution, and my second solution. The reason I'm going to do this is actually here we've got 2 pi, here we've got 4 pi, and actually my next one would be 6 pi, and the one after that would be 8 pi. So I now know that these pi's are going up in terms of, well, the even numbers, it would appear. So if I could find a way of describing these even functions, well, but this doesn't have pi on it, and this should be 0 pi and 0 pi. And actually, that's where we use a 0. So I can formalize this by saying, well, to get each of these pi values, I'm going to do 2n times pi. You're going to say, well, what's its value of n? N is going to be any integer value I can find. So when n is 0, 2n pi would become 0. There'd be 0 pi's. There'd be nothing. When n is 1, I'd end up with 2 pi. When n is 2, I'd end up with 4 pi. Hold on a moment. 2 pi, 4 pi. Those are the numbers I wanted. Yes. And if you look at each successive pair, one of them is plus pi on 3 and one of them is minus pi on 3. And we can coordinate this by doing plus or minus. And in this situation, it would be pi on 3. But actually, that's very specific to this one question. It's very specific to where I have cos x is 0.5. So can I actually replace this with a more general term? Well, I should, Coco, because if you remember, what did we do? Well, to get x in this situation, we did cos to the minus 1 of 0.5. If we had a more formal cos x is equal to a, for example, then we would know that each of my initial solutions would be found by cos a, cos to the minus 1 of a. And so, yes, I can make this more general to say that my solution set is given by 2n pi plus or minus cos to the minus 1 of a, where a is the 0.5, 0.3, or whatever it is they want us to find. A is this value of what they're trying to find us, what they're trying to ask us to find. Wow. And actually, ladies and gentlemen, that is the basis for making life so much easier for ourselves. This comes up in every VC exam, all right? You need to be able to understand that cosine basically needs this formula here. So I would be writing that in my formula book. The same is absolutely true for tan. If we are looking for tan to the minus 1 of, again, 0.5 in this situation, I would be drawing a line through y equals 0.5, and I would be reading off all of these values here. Now, how does that apply to the theory for what we've just done for cos? Well, how did we get between each successive solution in a tan graph? What do we know about the period of tan graph? Well, the period is actually pi. What was the period of a cosine curve? It was 2 pi. So if I know that it's got something to do with finding my initial solution and then adding on pi, we can use that to help us form this general equation. Right, so because I know what the inverse tan of 1 is, I'm just going to try and find where tan x is equal to 1. So first things first, tan to the minus 1 of 1, I know, is pi on 4. It's 45 degrees. So that is my first solution, pi on 4. We know, as I've said, to get to each successive solution, I would just add on pi on 4. So my first solution is pi on 4. My next one would be pi plus pi on 4. Then 2 pi plus pi on 4. And 3 pi and 4 pi. Not 3 pi. What am I talking about? I'm talking about tissues. And so if we were looking for the idea that this is going pi, 2 pi, 3 pi, 4 pi, that's got to be 0 pi, which means that this has an n of 0. Let's make that n of 1. Let's make that n of 2. And so lo and behold, that first part is given by simply n pi. All of these are just plus pi on 4. We don't have the plus or minus variant. And so actually, that would be plus pi on 4. for this particular example, but if we want the more general example, how did we find out that we had pi on 4? Well, yep, we replaced that with tan to the minus 1 of a, where this value here would be a. So my general solution is given by x is equal to n pi plus tan to the minus 1 of a. I am loving this. You're probably going to ask yourself, why did I leave sine till last? Why did I leave sine till last? Probably because it is the most challenging one to try and find solutions for. Not really, I just made that up. For sine, it is a little bit more complicated, but the theory is generally the same. So if I was having, again, sine of x equals a half, it says draw a line horizontally through y equals a half. Find the first solution. So x in this situation would be pi on 6. Now, if we were to use all stations to Canberra, what would we know? Well, the first one here is pi on 6, which would mean that this one here would also be pi on 6. Sorry for my bad handwriting. So this would be pi minus pi on 6. So that next solution would be pi minus pi on 6, which would be 5 pi on 6. There we go, 5 pi on 6. How would I get to subsequent solutions? I'd keep adding on pi on 6. Right, so going back to the maths, and we don't need the example here. We know my first solution was pi on 6, and my next solution was pi minus pi on 6. Then I would take this and add 2 pi to give me 2 pi plus pi on 6. And I would take this and I would add 2 pi on to give me 3 pi on 6. So I've got pi on 6, I've got 2 pi plus pi on 6, 4 pi plus pi on 6, and then my next solution would be 6 pi plus pi on 6. But unlike the cosine curve, my next one here would have been pi minus pi on 6. This would have been 3 pi minus pi on 6. And this one here would have been 5 pi minus pi on 6. Eesh, that's gross. So how do I now formalize this in terms of some sort of formula? How would I do this? Well, this would be 0 pi plus pi on 6. And what would this be? Well, this would be minus pi plus, minus pi minus pi on 6. So we notice if I was to split this in half, if I was to say here that n equals 0, and here n equals 1, and here n equals 2, and here n equals 3, why? Because we're only going to ever put n values as integers, right? So that's 0, 1, 2, 3, and negative values. So all of these have plus pi on 6. All of these have minus pi on 6. These are all my even numbers. We've already done that with the cosine, so that's 2m pi plus pi on 6. But how do I get the odd numbers? Remember, these are odd numbers, 1, 3, 5, 7, 9. Well, it just so happens, to gain the odd numbers, you do 2n minus 1. And there, ladies and gentlemen, are 2 equations to help me find the general solutions of sine. So yeah, there are 2 solutions. Now, while I say here that we've got 2n pi plus pi on 6 and 2n minus 1 pi minus pi on 6, we don't want that pi on 6, do we? Because that's for specifically this question. So that would be replaced by 2n pi plus sine to the minus 1 of a, and, not or, 2n minus 1 pi minus, and I've run out of room, sine to the minus 1 of a, which are these 2 equations here. So tan has 1 equation, cosine has 1 equation, sine has 2. How on earth do we use this stuff? Well, we use it like magic. Not really. First things first, when a question says find the general solution, it is asking you to use this specific theory. All right, so find the general solution for cos x. So first things first, I am looking for cos here, so I would write down what my general solution for cos was. X is equal to 2m pi plus or minus cos to the minus 1 of a. What was the value of a? Right, well, we would be looking for the cosine of x is equal to root 3 on 2. So I'm going to do x is equal to the cosine to the minus 1, the inverse cos of root 3 on 2, which I would use my calculator or the triangles or whatever else to find, and it just so happens that x in this situation is pi on 6. So I now absolutely just put that into my equation.
So x in this situation is equal to 2n pi plus or minus pi on 6. Now you might argue, well,
isn't that the answer? Yes, it can be, depending on what the question is asking you for. But generally speaking, it seems to want you to take one extra step by combining this into a simpler formula to use. And that's what it's going to do. And why? How do we do that? Well, we basically put this into one fraction. So combining both of these fractions into one, that would give us x is equal to, well, putting this over a common denominator of 6, that would be 12n pi. Write it all over 6 gives me 12n pi plus or minus pi. And because I've now got two terms with a pi in it, I can effectively say, let's actually write it here, x is equal to, take out pi, so 12n plus or minus 1 pi on 6. If the question actually wanted the solutions, you're going to try and say, well, how would I then find the solutions? Well, if you remember back to the theory, this value here, this n value, is an integer value, right? And so you would write n is in the set of real numbers. Because n can't be real, sorry, I said real numbers, I meant integers. N can't be real numbers. That would make no sense, right? We're looking for solutions. And so the first thing I would say is, well, when n equals 0, what would I have? Well, I'd have 12 times 0, so putting n equals 0 into this equation, 12 times 0 is 0. So I would have plus or minus pi on 6. Oh, awesome. So that's given me two of the solutions, either side of the y-axis. Then I'd put n equals 1 in. And what would I end up with? Well, 12 times 1 is 12, plus or minus 1. So 12 plus 1 would be, so I'd end up with 13 pi on 6 and 11 pi on 6. See what I'm doing here? 12 plus 1, 12 minus 1 gives me my solution. So just by putting those two values in, 0 and 1, I've got 4 solutions. I actually think this is quite clever, quite helpful as well. Here's another example. Find the general solution for tan 2x equals 1. Same thing happens here. My advice to you is ignore the 2x for the moment. Why would I ignore the 2x? Well, the general solution actually works with the standard tan graph. So if you remember the general solution for tan, it was n pi plus tan to the minus 1 of x. That was for my standard tan graph. So I'm going to do that. So I'm going to say, what is the inverse tan of 1? Well, we've already done that. That was nice and easy. It was pi on 4. So my general solution for the general tan graph, for the specific tan graph, would have been x is equal to n pi plus pi on 4. But this isn't the tan graph. It's the 2 tan graph, which basically means that my period, not my period, that my amplitude has changed. So rather than writing x equals, I'm actually going to write 2x equals, because I need to take my original solutions and halve them. Why? Because my period is halved. Get it? So now I can say that x is equal to n pi on 2 plus or minus pi on 8. And as we've done previously, I would write that as x equals, put it over a common denominator of 8, 4n pi plus, why did I put plus or minus? Come on down, stay with it. I know you've recorded 14 lessons today, but come on. Plus pi, which we would then put as a common denominator, would factorize out to give us 4n plus 1 pi on 8. And again, how would we use this? How would this be important to us? Well, again, we would have to say here that n is in integers. And so, knowing that I would generally start with n equals 0, but n equals 0 in here, what do I have? I'd have pi on 8. And then put n equals 1 into my equation. What would I have? 5 pi on 8. And then n equals 2. Now, again, I'm going to put n equals 2 in here, but let's say 9 pi on 8. Remember, n can be negative. N can be minus 1. So you'd end up there with minus 4 plus 1, which would be minus 3 pi on 8. These are equally valid. Now, you're going to say, well, how do I know which values of n to use? Well, remember, the question would, generally speaking, ask you to then go on and maybe find the solutions between maybe minus pi and pi. Well, having put in the values here, I would just then pick out which ones would be valid to me between minus pi and pi. So that one would be valid, that one would be valid, that one would be valid. And so this formula saves me a huge amount of work. Last one, find the general solution for sine x equals a half. I'm not going to go through all the working here other than to say that actually there are two equations. So we would need to do sine to the minus 1 of a half, which we now know is pi on 3. And I would substitute that into both of my equations. So it does appear that I'm actually going to do this. I know I just said I wouldn't do this, but I'll do it. So my equation 1 gives you x equals 2m pi plus pi on 3, and x gives me 2n plus 1. And just going to go back to what I explained up here, because that should be a plus. Okay, so I'll edit that later. I'll put something in there later. Whoa. But otherwise, going back to this, 2n plus 1 minus pi on 3, which you would then put over and make common denominators that we have done here, right? So that in its simplest form or in an easier form would give me that. Don't forget that if you put this as a general solution, you'd have to say that n is in integers. And again, n is in integers, right? That's a z with 2 lines in between. I'm not very good at drawing that today, all right? So how would we use these results? As I said earlier in one of those questions, if we knew that we had found out the general solution and we'd already done cos to the x is root 3 on 2, that was our general solution. We would then just put the values of n equals 0, 1, and 2 in, and that would pop out my first 3 positive solution. In fact, it would give me lots of solutions. Yes, it would actually give me lots of solutions, but you would be looking to find the first 3 positive solution. Likewise, if we were going to try and find the first 3 positive solutions for sine as a half, these were my general solutions. When I put in the values of n equals 0, 1, and 2, out came these 3 solutions for the first equation and these 3 solutions for the second. Now it's up to you to then put them in order. So obviously if we put these in order, you know, pi on 3 would be first, then 2 pi on 3, then 7 pi on 3, and 8 pi on 3, and 13 pi on 3, and 14 pi on 3. But because it only wants the first 3 positive solutions, we would discount. What would we discount? 7 pi on 3. So our solutions would be, no, that's not true. I discounted 8 pi on 3. I can't even read my own handwriting anymore, to become 7 pi on 3. Okay, this is not my usual flair. Sadly, yes, I've recorded something like 15 lessons today, and you can probably hear my throat is giving out. So that is general solutions for sine, cosine, and tangent. All right, thanks very much for watching. I look forward to seeing you next time. Joining us for that video. It was really good having you. Now, if you'd like to know when the next video is coming, why not click on subscribe? Alternatively, head on over to MaffsGuru.com where you can watch all of the videos on its own dedicated website. While otherwise, watch the video that's just popped up. It'll be part of this series. All right, take care. See you again soon.